Hello guys, in this video I'm going to show you how to obtain this result using the Feynman trick, right? So this is a parameter dependent integral. So this integral, I'm going to rewrite the integral like this. I'm going to introduce another parameter b, and that is going to be the integral from 0 to infinity of what? ln of 1 plus b times x squared, right? Divided by a squared plus x squared dx. Right, so this is the parameter I'm introducing. We see that this integral that I introduced, I of b, this is the same as the original integral I, if and only if b is equal to 1. Right, so we just have to solve this one using the Feynman trick, and then we'll just replace b with 1, and that will be the proof. So good luck with the Feynman trick. So let's start with the Feynman trick, which is the differentiation under the integral sign. I'm going to differentiate this with respect to the parameter that I introduced, I of b, and that is equals to the integral from 0 to infinity of differentiating with respect to the parameter, which is the ln of 1 plus bx squared, right, all over a squared plus x squared dx. All right, cool. Now the left hand side is I prime of b, and that is equals to the integral from 0 to infinity of, now differentiating this one is 1 all over what is already at the bottom is a squared plus x squared. This is now multiplied by 1 plus bx squared, right? And then we will have to differentiate this with respect to b and multiply. That is going to be x squared dx. All right, so this is the same as the integral from 0 to infinity of x squared all over, right, a squared plus x squared, a squared plus x squared. This is multiplied by 1 plus bx squared, right, dx. Cool stuff. And now here we now have to differentiate this using partial fractions, right? So this one is x squared all over x squared plus a squared, right? This is multiplied by 1 plus bx squared, right? So using partial fraction decomposition, we are going to have ax plus b, right, divided by the first quadratic term, x squared plus a squared, and then the next term is going to be cx plus d, and this is going to be divided by 1 plus bx squared, like this. So now x squared all over x squared plus a squared, and then 1 plus bx squared. This is the same as what? So we are doing cross multiplication, ax plus b multiplied by 1 plus bx squared, and then cx plus d, this is multiplied by x squared plus a squared. All this one divided by the denominator, which is the LCM, the product of these quadratic terms. All right, cool. Now the denominators are the same, so the task is to make the numerators the same as well. So let's FOIL this on top. That is going to be ax plus b times ax to the third, right, plus b plus small b capital B x squared, right? Now this is going to be cx to the third, right, plus a squared c times x plus dx squared, and then plus a squared d. So this is what we have after the expansion. Now let's gather like terms and do comparison. So you have b times a and then plus c. All these ones are the coefficient of x to the third, this and this, right? Next is x squared terms, that is small b capital B plus d. This is x squared, that is this one and this one, right? Next is going to be what? This is going to be plus the x terms, that is going to be a and then small a capital C. This one is x terms, this and this. And the last one, the constant terms, we have b and then a squared d, right? Now let's do comparison. So we have b, a plus c. This is equal to 0. The coefficient of x to the third on the left is 0. We have b plus d. This is equals to 1, equation 2. The coefficient of x squared on the left hand side is 1. That is here. And then we have a plus a squared c. This is equals to 0. The coefficient of x on the left hand side is 0. And the constant term b plus a squared d. This is equals to 0 as well. The constant term on the left hand side is 0. Now solving these four equations simultaneously, these are the values of a, b, c, and d that will satisfy them. So a is going to be 0, b is a squared, right, all over a squared b minus 1. C is equal to 0 and D is equal to negative 1 all over a squared b minus 1. These are the values of a, b, c, and d that will satisfy all the four equations. And now the partial fraction will now look like this. So we are just going back here and we are just replacing the values. So x squared all over x squared plus a squared multiplied by 1 plus bx squared. This is the same as ax plus b all over the first factor. So a is 0, so 0 times x is 0 plus b, so that is going to be b is a squared all over a squared b minus 1. This one is divided by the first factor, x squared plus a squared. And then plus cx plus d, c is already 0 plus d, and d is going to be negative 1 all over a squared b minus 1. This is divided by the second factor, which is 1 plus bx squared. Right. So this is x squared all over x squared plus a squared. This is multiplied by 1 plus bx squared. And this is the same as a squared all over a squared b minus 1. This is multiplied by 1 all over x squared plus a squared. And then minus 1 all over a squared b minus 1. This is multiplied by 1 all over 1 plus bx squared. Right. So now if you can recall, the integral I prime of b is the integral of this, right, which is what we have here. All right. So the integral, let me switch again. The integral I prime of b is equal to the integral of this one. So that is going to be the integral of this, because they are the same, which is a squared all over a squared b minus 1 times 1 all over x squared plus a squared dx, minus the second one is going to be is from 0 to infinity. Sorry about that. So this is 1 all over a squared b minus 1 times 1 all over 1 plus bx squared dx. Cool. So this is the partial fraction decomposition. This one is a constant. It has nothing to do with x. A squared all over a squared b minus 1. The integral from 0 to infinity of 1 all over x squared plus a squared. This integral is familiar, right? Minus 1 all over a squared b minus 1, because it's a constant. The integral from 0 to infinity of 1 all over b here, I'm going to factorize it out. And what is left here is x plus 1 over b, right? And then dx. But 1 over b permits me to write it like this. This 1 over b, I'm going to write it like this. That is 1 over the square root of b, all this one squared. Alright, now let's compare this one to the arctan integral. If I have the integral of 1 all over x squared plus a squared dx, this is the same as 1 over a and then the arctan of x over a plus the constant of integration. Okay, so I prime of b is equal to what? We have a squared all over a squared b minus 1, and this is, now integrating this is 1 over a, which is multiplied by the arctan of x over a, the limits of integration from 0 to infinity, minus 1 all over a squared b minus 1. This is multiplied by 1 over a, here is 1 over the square root of b, and then we have the tan inverse of x all over 1 over the square root of b, the limits of integration from 0 to infinity as well. I prime of b, this is equals to, this will cancel one of it, leaving a on top, a squared b minus 1 at the bottom. And now let's take the limit as x approaches infinity of the tan inverse of x over a, minus the lower limit, tan inverse of 0 is 0, because when you plug in 0 here, it becomes 0, minus, simplifying this one is the square root of b all over a squared b minus 1, right? And we are making a mistake here, so this one will come here, so I forgot about that. So the b is going to multiply out, right? So this b is multiplying out here. I forgot to pull it out, I'm sorry about that. So there's b here which is multiplying. All right, and then we are going to have the limits, right, as x approaches infinity of the tan inverse of the square root of b times x, right, minus plug in 0, tan inverse of 0 is 0. All right, so I prime of b, this is equals to, we have a all over a squared b minus 1, and as x is approaching infinity, tan inverse of infinity is going to be pi over 2 minus this one, rationalizing this and this, that becomes what really? That becomes 1 over the square root of b, and this is multiplied by a squared b minus 1. All right, and as x is approaching infinity, the tan inverse of infinity is pi over 2. All right, so that is multiplied by pi over 2. Alright, cool. Now you see that pi over 2 is common between the two terms. I'm going to pull it out, pi over 2. And now we have a all over a squared b minus 1 minus 1 all over the square root of b. This is multiplied by a squared b minus 1, like this. We want I of b, not I prime of b. So what I can do is to take the antiderivative, right? So I'm going to integrate I prime of b with respect to the parameter b, and that is going to be equal to pi over 2. Then I'll integrate with respect to b as well on the right hand side, a squared b minus 1 dA, right, minus the integral of 1 all over the square root of b multiplied by a squared b minus 1 dB. I'm sorry, this is b. All right, so that is differentiating, integrating with respect to the parameter b. Now the integral of the I prime of b is the I of b, and this is equals to pi over 2, right? And now how do I integrate this? So for the first one, what I can do is that if I differentiate this one with respect to b, I have a squared, right? So I have to get a squared at the top, right? So for me to do that, I have to multiply this numerator by a and nullify the effect by dividing the integral by a. So when I do that now, the integral now looks like this. So I have 1 over a, the integral of a squared all over a squared b minus 1 dB, minus the integral of 1 all over the square root of b multiplied by a squared b minus 1 dB. So you see that now when I differentiate the denominator, I get the numerator, and the resulting value of that integral is this. So pi over 2 multiplied by 1 over a, and this is now the ln of a squared b minus 1, right, minus this integral, the integral of 1 all over the square root of b multiplied by a squared b minus 1 dB. I'm going to do a trig sub here. All this one is multiplied by pi over 2 in front. So now let's do a trig sub for this integral. So we are going to let's say b to be equal to, this is a substitution that I'm using, secant square of theta over a squared, right? So when I do that, dB is going to be differentiating with respect to the theta. That is now going to be 2 secant of theta times the derivative of the secant of theta, which is the secant of theta tangent of theta d theta. All this one is divided by the a squared, the constant. So the b is going to be 2 secant square of theta tangent of theta d theta all over a squared. So in place of this, I'm going to replace with that. Now what about a squared? So what about the square root of b? I'm sorry, square root of b is the square root of the secant square of theta over a squared, and that is equals to the secant of theta over a. As simple as this. What about a squared b minus 1? So a squared b minus 1, this is the same as a squared, b is this, right? So that is a squared multiplied by the secant square of theta over a squared minus 1. And this is the same as the secant square of theta minus 1, because this and this will cancel pretty nicely. And now from the Pythagorean identities, we know that the secant square of theta minus 1 is the same as the tangent square of theta. So a squared b minus 1 is the tangent square of theta. So that means that the square root of b multiplied by a squared b minus 1, a squared b minus 1, this is the same as this one multiplied by the tan square of theta. So that is the secant of theta, the tangent square of theta, all over a, right? So now we can take the integral into the theta world and see how it looks. So I of b is equal to pi over 2, and this is multiplied by 1 over a, right? And then the ln of what? A squared b minus 1, a squared b minus 1, right? And then minus the integral of 1 all over, square root of b multiplied by a squared b minus 1, which is this, right? So which is the secant of theta, secant of theta, the tangent square of theta all over a, and this is multiplied by db. An expression for db is that, which is 2 secant square of theta, tangent of theta, d theta, all over a squared. This is closed with a square bracket. So far so good. I of b is equals to pi over 2, right? Then 1 over a, and then we have the ln of a squared b minus 1 minus, there's going to be a lot of cancellation here. So this a is going to cancel 1a squared here. There is secant of theta, which is cancelling 1 secant of theta. There is tangent of theta here, which is cancelling 1 tangent of theta, right? So what is left? So this is 2 over a now, which is left. This 2 and this a here is now left, which I'll bring out because it's a constant. And then the integral of what is left on top here is the secant of theta. And what is left at the bottom is the tangent of theta, d theta. Right, so let me simplify secant of theta over tangent of theta and see what it is. Secant of theta over the tangent of theta. This is equals to secant of theta is the 1 over the cosine of theta, and tangent of theta is the sine of theta over the cosine of theta. This will cancel this, and that is left with 1 over the sine of theta. And 1 over sine of theta is equals to the cosecant of theta. All right, so this one, I'm going to replace this one with the cosecant of theta. I of b is equals to pi over 2. This is 1 over a, the ln of a squared b minus 1 minus 2 over a, then the integral of the secant of theta. The cosecant of theta, d theta. How do you integrate the cosecant of theta? This, I'm just going to write the resulting value of the cosecant of theta. This is the ln of a squared b minus 1 minus 2 over a. Then the integral of the cosecant of theta is the ln of the cosecant of theta, ln of the cosecant of theta minus the cotangent of theta, like this. So we are done with the integration. You can put the constant of integration. Now let's go back to the b world, because the integral must be in terms of b, right? So now we are going back to the substitution. The substitution that b is equal to the secant square of theta over a squared. So let's go back there to help us move back into the b world. So b is the secant square of theta over a squared, right? So we can find secant of theta here. So that means a squared b is equals to the secant square of theta, implying that secant of theta is equals to the square root of a squared b. So secant of theta is equals to a times the square root of b, right? This is the same as this over 1. So now that we have this, we can draw a right triangle, right? I love to always do it on a right triangle. So the angle here is theta, and now this is the right angle. So secant of theta is hypotenuse over adjacent. The hypotenuse is always a line opposite to the right angle, which is a square root of b, and adjacent is 1. Now we have to find the opposite. You can call it m if you like. So using the Pythagoras theorem, m squared plus 1 squared is equals to the square of the hypotenuse, right? So this is the Pythagoras theorem. So m is equals to a squared b minus 1. So that means that m is equal to the square root of a squared b minus 1. So this m is equals to the square root of a squared b minus 1, like this. So now that we have this, we can now find sine of theta, cosecant of theta and cotangent of theta, right? So the cosecant of theta is equals to what really? So the cosecant of theta is equal to hypotenuse over opposite, right? The hypotenuse is a square root of b all over the opposite is the square root of a squared b minus 1. And then we can find the cotangent of theta as well. So the cotangent of theta is equals to adjacent over opposite, 1 all over the square root of a squared b minus 1, like this. So we have all of this in terms of b. We can now take the integral into the b world completely. Okay, so I of b is equal to what? Pi over 2. This is multiplied by 1 over a, and then ln of a squared b minus 1. Cool. Minus 2 over a, and then the ln of cosecant of theta minus cotangent of theta. Cosecant of theta is a square root of b all over the square root of a squared b minus 1, all over the square root of a squared b minus 1, minus the cotangent of theta is 1 all over the square root of a squared b minus 1, plus the constant of integration. Now let's simplify this. The calculus is done. This is now algebra. Pi over 2. Now what do we have? 1 over a, the ln of a squared b minus 1 minus 2 over a, the ln of this is a square root of b minus 1. All this one is divided by the square root of a squared b minus 1, plus the constant of integration. Okay, so this is what we have. So now we can apply some laws of logarithm here, right? Before we do that, let's bring this 2 here to the power using the power rule of logarithm. So let's do that. I of b is equals to pi over 2. This is multiplied by 1 over a times the ln of a squared b minus 1 minus 1 over a here as well. Then the ln of a times the square root of b minus 1. This is squared, right? All this one too is divided by the square of this one. So the square of the denominator is just going to remove the square root. That is going to be a squared b minus 1, plus the constant of integration. All right, so because this square is going to remove the square root, that's what we have. And now we can apply some laws of logarithm there. So I of b is pi over 2, and then 1 over a, the ln of a squared b minus 1 minus 1 over a. This is the ln of a square root of b minus 1. This is squared, and then minus the ln of a squared b minus 1, like this. All right, plus the constant of integration. All this one is multiplied by 1 over a in front. So I of b is equals to pi over 2, and then 1 over a, the ln of a squared b minus 1 minus 1 over a, and then the ln of a square root of b minus 1, like this. This is squared, and then plus 1 over a, because negative plus 1 over a, the ln of a squared b minus 1, plus the constant of integration. Now we see that this and this are the same, so we can combine them. All right, so I of b is equals to pi over 2, and now this and this are the same, so that's just 2 times of that, so that is 2 over a, the ln of a squared b minus 1, and this one, I can also bring this 2 back here again, right? I'm bringing the 2 back using the power rule of logarithm, and that is going to minus 2 over a, and then the ln of a square root of b minus 1, like this. All right, we are almost there. So this one, 2 over a, is common between the two terms, right? So we can factorize it out. So we have pi over 2, and we factorize 2 over a out, and then we are going to have the ln of a squared b minus 1 minus the ln of a square root of b minus 1, like this. Okay, so I of b is equal to, this cancels that, we have pi over a, and then applying the power, the laws of logarithm, we have the ln of a squared b minus 1. This is divided by a times the square root of b minus 1, like this. All right, so this is what we have. I'm going to clean this one and just bring it closer. Okay, so this is pi over a, like this. So this is what we have all along. I forgot the constant, forgive me for that, plus the constant of integration. Now we have to find the constant, right? So let's put b to be equal to 0, right? When b is equal to 0, we have I of 0, and that is equals to pi over a, and then the ln of when b is 0, this is 0 and this is 0, right? So that is going to be the ln of -1 over -1 plus c. -1 over -1 is 1, and then I of 0 is pi over a times the ln of 1 plus c. So that means that c is just equal to I of 0. But what is I of 0? When we replace the parameter b with 0, what are we getting? So we can go back to our original integral, right? So when we go back to our original integral here, when b is 0, everything becomes 0, right? Because you now have ln of 1 on the numerator, which is 0. So I of 0 here is equal to 0, right? So when we go to the bottom there, that is down there, we will have this. So I of 0 is equal to 0, and that is equal to c. So it means here c is going to be equal to 0, right? So now that c is equal to 0, we can replace it. I of b is equal to pi over a, and then the ln of a squared b minus 1 all over a square root of b minus 1, like this, and c is 0. Now we have to now find the original integral. So the original integral, remember when I started, I said that the integral I introduced is equal to the original integral if and only if b is equal to 1, right? So if and only if b is equal to 1, this integral ib is the same as our original integral. So I'm just going to replace b with 1 in the final result, and then I can get the proof, right? So just replace b with 1, and that will be the proof that we are required to show. As simple as that. So here I of 1, that is replace b with 1. So here b is equal to 1. Put b to be equal to 1, and that is going to be pi over a. This is multiplied by the ln of a squared minus 1 all over a minus 1, like this. All right, so I of 1 is the same as I. So I of 1, when b is equal to 1, that's the same as I. So here I is equal to pi over a, and then the ln of, this is difference of two squares, the numerator, which is a minus 1 multiplied by a plus 1 divided by a minus 1, like this. And this one is going to cancel this one out nicely, and that is left with the proof, pi over a, the ln of 1 plus a. This is the proof that we are tasked to show. So that is how I solve this integral. So these integrals, they are quite demanding, but when you realize that, you have to apply the Feynman's trick, introduce another parameter which will help you to solve this integral quite nicely. The integral will become very easy for you to integrate. So that is how I prove this integral. If you know an alternative version to solving this integral, which is quite faster than this, I would urge you to put your comment in the comment section and let me know what you think. And if you really enjoyed the video, consider subscribing to Calculus Diaries and give me a thumbs up so that I'll continue uploading engaging tutorials on integrals and calculus in general. I thank you so much for watching this video, and I'll see you in the next one. Bye bye.